In the last video, we discussed average velocity and said that we get instant velocity by taking some limit. So what is a limit? When we make a limit statement, like the limit of the function f(x) as x approaches c equals L, it's written with this notation. And what it means is that we can get the function f of x to be as close to L as you want by making x stay very close to c. More precisely, for any tiny allowable amount of error, which we'll denote with epsilon, there is some tolerance level, delta, so that if x is within delta of c, then the output, f of x, is within the margin of error around L. So the difference between f, x, and L is less than epsilon. Pictorially, we're saying that if you want f of x to stay inside some little strip around L, you'll be able to accomplish that by making x stay within some strip around c. This tiny portion of the function between the two pink lines stays inside of the two blue lines. So whenever x is between c minus delta and c plus delta, then f of x is between L minus epsilon and L plus epsilon. The book goes into detail about this definition in section 2.9, which is not on the syllabus for this class. But you do need to internalize this definition enough that you can recognize when a limit exists and when a limit does not exist. Let's see some examples. In the last video, we calculated the average velocity of an object dropped according to Galileo's formula. When we looked at the average velocity on some interval from a time t to 1 second, the formula for the average velocity was this. What we concluded can be stated with the following limit. The instantaneous velocity of the object after 1 second is the limit of the average velocity, where we're taking a smaller and smaller interval by letting t approach 1. When we do this, the result is an instantaneous velocity of 9.8 meters per second. We verified this numerically by looking at values of t really close to 1, but we can also verify it algebraically as follows. When we factor the numerator, we see that a 1 minus t comes out. If t is literally equal to 1, then this factor is 0, and we can't really cancel the 0 from the numerator and the denominator. But if t is any other number, even if it's really close to 1, so this factor is a really tiny number, it's okay to cancel it. So we get that the average velocity over any interval with any positive length is going to be 4.9 times 1 plus t. Clearly, if we take t to be really close to 1, this quantity is going to be really close to 4.9 times 2. This idea of factoring is going to be an important strategy for computing troublesome limits when we get to section 2.5. I claim that if you take the limit of sine x as x approaches 3 pi over 4, you'll get the square root of 2 over 2. Why is that? If you put any strip around that limit, L equals square root 2 over 2, then I'll be able to put some little strip around 3 pi over 4, which makes my function stay inside of your strip. Even if you reduce the allowable amount of error, so you make your strip narrower, then I'll also be able to succeed by making my strip narrower. Square root of 2 over 2 is about 0.707. If I make any other limit statement here, even if it's very close, like that this limit is 0.75, it's going to be false. Why is that? If you zoom in close enough and you choose epsilon to be really small, like 0.01, then the epsilon strip around this candidate limit, 0.75, is not going to include square root 2 over 2. And that means no matter how tiny of a strip I put around c, I put around 3 pi over 4, there's still going to be some function values here which are not inside of the blue strip. We know really the limit should be square root 2 over 2. So when x is really, really close to 3 pi over 4, I'm getting values really close to square root 2 over 2. And since they're really close to square root 2 over 2, they're not really close to 0.75. There's a gap. And we can't avoid this gap just by pushing these two pink lines closer and closer together. We'll still have a little segment of the function which is outside of that blue error bound. Notice that in this example, the correct limit equals sine of 3 pi over 4. That's not an accident. This is called the substitution method, where we just plug the thing that x is approaching into the function and hope that what pops out is the correct limit. We'll see in section 2.4 when this works and when it doesn't work. Please go on to the next video where we'll see what it looks like when a limit doesn't exist at all.